The last class we started with induction motor control, speed control of induction motors. यहाँ पे मैंने आपको बताया कि there are two methods of speed control. One is the scalar control strategy and another one is the vector control strategy. And there's a third control strategy that's a direct torque control. That is somewhere in between the scalar control and vector control strategies. So we'll be starting first now with the scalar control strategy. So as already indicated, scalar simply means magnitude variation. So scalar control basically deals with Scalar control basically deals with magnitude variation of uh, the parameters. So by changing the magnitude of voltage or current or frequency, we can control the speed of torque, position, flux, etc. of an induction motor. So as far as the scalar control goes, it's fairly simpler as compared to the vector control strategy. Uh, but although it's simple, the accuracy of this control accuracy or we can say efficiency of this control strategy is poorer as compared to the vector control strategy. Now, why the efficiency of scalar control strategy is poorer as compared to uh, vector control strategy is owing to the fact that in case of induction motors, the flux and torque they are dependent. Uh, they are dependent upon each other. That means इंडक्शन मोटर्स में क्या होता है कि आपका जो फ्लक्स है that's also dependent on voltage as well as on frequency. Similarly, torque is dependent on both voltage as well as on frequency. So if we are changing one parameter, say for example we are trying to achieve torque control, flux will also get automatically changed in the system. Or if we are changing the flux, torque will also get changed in the system. So this dependency actually means that the two loops, the torque loop and the flux loop, the torque loop will be dependent upon how the flux is behaving in the system. As far as the flux is concerned, I have already stated to you that flux response is pretty sluggish as compared to the torque response. Flux rises very slowly as compared to torque. While as we want our torque, we want our speed response to be very fast. We want a dynamic speed oblique torque response. But because of the dependency on the flux in case of induction motors, uh, this is a disadvantage associated with AC machines. This is not seen in case of DC machines. DC machines with flux and torque they are independent of each other, but in case of AC machines, flux and torque they are dependent upon each other. Since flux response is sluggish, that makes the torque response, or we can say the speed response, also sluggish in case of induction motors. So in short, we can say that scalar control does not cater to or does not take into account the flux and torque coupling in case of induction motors. Fine. So scalar control, it is simple. Although it is simple, it does not take into account the flux and torque coupling. That's why its efficiency is poorer, its accuracy is poorer as compared to vector control. So it's not as robust as the vector control strategy is, that we'll be studying later on. As far as the scalar control goes, it depends, or it we can say it utilizes the equivalent circuit model of. It simply uses the equivalent circuit model of induction motor, or what I described in the last session as well, as a steady state model of induction motor. So using the equivalent circuit, we can basically see how speed variation is achieved in case of induction motors, how torque variation is achieved, how the how we can calculate different steady state parameters of the system. For example, the losses, the efficiency, extra. So for that, we make use of the equivalent circuit model of the induction motor. So scalar control, it's simply magnitude variation. We can change the magnitude of voltage or current to achieve control of speed, torque, or position. It's simpler. Its accuracy, its efficiency is poorer as compared to the vector control strategy, owing to the coupled nature of flux and torque in case of induction motors. And it uses simply the equivalent circuit model of the induction motor. What are the different types or the methods of scalar control strategies that we can employ to control the speed of induction motor? So first one is starter voltage control. Right? Uh, so by changing the voltage of the uh, starter, by decreasing the supply voltage, we can actually decrease the speed of an induction motor. Right? Also, by reversing the phase sequence of induction motor from ABC to BAC, say for example, we can make the motor operate in an anti-clockwise direction. So by simply changing the starter voltage, we can increase or decrease the speed of induction motor. So this you have already studied in case of machine schools, and you may have also practically done these uh, So one is simply the starter voltage control. Second one, uh, the rotor voltage oblique current control. So if we can decrease the induced voltage in case of in case of in the rotor of the induction motor, we can again uh, control the speed of induction motor. Or what we can do is simply by increasing the resistance. In case of a wound round induction motor, we can increase the rotor resistance such that the current changes, and as the current changes, we can achieve lower speeds or higher speeds according to how we are changing the rotor resistance. Either uh, normally we'll be able to put the rotor resistances in series, so that will only mean the current can be decreased. उससे आपकी speed कम हो जाएगी. But if we can also put the resistances in the rotor side in parallel, we can decrease the rotor resistance, we can increase the current, rotor current, we can accordingly change the speed of induction motor. So again, by changing the rotor resistance or by decreasing the induced voltage in the rotor, we can control the speed of induction motor. So these are simply magnitude variations. We are simply changing the voltage magnitude. We are simply changing the voltage magnitude in the stator, in the rotor, or we can, another method will be frequency control method. As far as the induction motor goes, you know the synchronous speed is 120 F by P. So either by changing the number of poles, you can uh, change the synchronous speed, or by changing the frequency of the supply voltage, fine, you can change the synchronous speed. As the synchronous speed changes, the rotor speed will fall, will change as well, fine. So if you are increasing the supply frequency, जो आप starter voltage दे रहे हो, if you are supplying it at higher frequency, you can achieve higher synchronous speed. If you are if the supply voltage uh, is being fed at lower frequencies, you can decrease the synchronous speed. सिंक्रोनस स्पीड कम होने का मतलब है कि आपकी रोटर स्पीड भी कम हो जाएगी, ठीक है. The rotor speed will always be less than the synchronous speed of induction motor. So if you are changing the synchronous speed, accordingly your rotor speed will also vary. So again, frequency control is uh, can be achieved either through power electronic devices, or you can use rotary machines to obtain frequency control. ठीक है. आप एक ऐसी मशीन डिजाइन कर सकते हो, एक ऐसा जनरेटर डिजाइन कर सकते हो जो आपको डिफरेंट फ्रीक्वेंसी लेवल्स पे वोल्टेज आउटपुट दे सके. एंड यूजिंग दैट generator, you can supply the induction motor to get to obtain different frequency for different synchronous speeds, to obtain different rotor speeds as required. Starter voltage control, rotor voltage control, frequency control. Fourth one is starter voltage and frequency control. Starter voltage and frequency control, uh, or what is also known as variable voltage. Variable voltage, variable frequency, or simply volt hertz control. So all of these scalar control strategies are simply magnitude variations. Now this fourth one, variable voltage, variable frequency control, it's one of the most widely used scalar control strategy. Now why it's preferred over other scalar control strategies? We'll see why. Uh, what happens in variable voltage, variable frequency control is what normally happens in case of an induction motor is that flux is proportional to voltage and flux is inversely proportional to frequency. Fine. So if we are using voltage control method uh, to change speed, or if we are using frequency control method to change speed, so while we are changing speed, flux also gets changed. Fine. इंडिविजुअली अगर हम बात करें, अगर हम वोल्टेज कंट्रोल खाली कर रहे हैं स्पीड कंट्रोल अचीव करने के लिए, आपका फ्लक्स भी वैरी हो रहा है एंड फ्लक्स इज डायरेक्टली प्रोपोर्शनल टू वोल्टेज. सो इफ यू आर इंक्रीजिंग voltage, your flux will increase, and increasing voltage also means increasing the speed of induction motor. Or if you are going for frequency control ऐसा है, if you are increasing frequency, your speed will increase. But if you are increasing frequency, simultaneously your flux will decrease. Flux is inversely proportional to the frequency of supply voltage. ठीक है? This is supply voltage, this is supply frequency. So both supply voltage as well as supply frequency, they can be individually used to control the speed of induction motor, but simultaneously flux is also getting varied. This I have already pointed out to you that the flux and speed, they are dependent, they have an interdependency in case of they are coupled to each other in case of an induction motor or in case of any AC machine in general. It's also true for a synchronous machine. Flux and torque oblique speed, they are uh, coupled to each other. So if you are changing the torque, flux will also get varied. If you are changing this, uh, if you are changing the flux, this torque will also get changed. Fine. So now we can basically combine the advantage of these two controls. One is the stator voltage control, another one is the stator frequency control, in such a fashion that the ratio V by F is maintained constant. So if the ratio V by F is constant, so while increasing the voltage, flux is increasing, but while increasing the frequency, flux is decreasing. That means our flux will remain constant in this machine. Why? So we are increasing voltage, we'll be increasing the frequency such that the ratio V by F remains constant, such that flux remains constant. But while changing both these two parameters, what happens is the speed, since speed is proportional to both voltage as well as frequency, so even if we are increasing voltage as well as frequency, speed will definitely change. So what we are doing here is we are increasing the voltage, we are increasing the frequency. So by both methods, speed will increase, but we are increasing the voltage and we are increasing the frequency in such a fashion that the ratio V by F remains constant. So variable voltage, variable frequency control is uh, V variable voltage, variable frequency control is actually performed to control speed as speed is directly proportional to both voltage as well as frequency, but simultaneously maintaining the ratio V by F constant such that flux remains constant. Speed is directly proportional to voltage and frequency, but as far as the flux goes, flux is proportional to voltage but inversely proportional to frequency. So if we change V by F in such a fashion that the ratio of V by F always remains constant, we can maintain the flux constant, but the speed will change. Fine. Similarly, we can decrease V, we can decrease frequency such that the speed will decrease, but the ratio remains constant such that flux remains constant. So this makes somewhat so this variable voltage, variable frequency control somewhat helps us achieve decoupling between flux and torque. So we can say variable voltage, variable frequency control helps us to decouple flux and torque. Why? Torque means actually the speed. I'll write here somewhat. So variable voltage, variable frequency control helps us to somewhat decouple flux and torque such that while we are actually controlling the speed, the flux does not change in the system. We have seen so four methods of scalar control strategy so far. One was the starter voltage control. Simply increase the voltage, speed will increase, decrease the voltage, speed will decrease. But while you are actually changing the voltage, flux will also change. So that means actually we are not keeping in mind uh, the flux at this time. So since flux is changing, speed will be affected. Flux variation is sluggish. That means speed variation will also become sluggish. Similarly will be the case with rotor voltage control. Similarly will be the case with frequency control. We can increase the frequency, we can increase the speed, we can decrease the frequency, we can decrease the speed, but simultaneously what is happening is that the flux is also changing. Flux is inversely proportional to frequency. So if you are increasing frequency, flux will decrease. That means जब तक फ्लक्स नेक्स्ट अपने स्टेडी स्टेट वैल्यू पे नहीं आ जाता तब तक स्पीड भी अपने स्टेडी स्टेट वैल्यू पे नहीं आएगा एंड सिंस फ्लक्स रेस्पॉन्स इज sluggish फ्लक्स रेस्पॉन्स इज स्लो दैट मीन्स आपका स्पीड रेस्पॉन्स भी स्लो हो जाएगा so that's a disadvantage with the coupling between flux and torque. We cannot independently control flux or the torque of the induction machine. Now, to achieve that decoupling within the scalar control framework, what we had so one of the methods that was suggested was starter voltage and frequency control, or what is known as the variable voltage, variable frequency control. So in case of variable voltage, variable frequency control, what we are doing is we are changing the voltage, we are also changing the frequency, but we are keeping the ratio V by F constant. Since flux is directly proportional to voltage and inversely proportional to frequency, that means by making this variation in such a way, flux will remain constant. So speed variation will be achieved, but flux will remain constant in the system. So somewhat we have been able to decouple flux and torque using the variable voltage, variable control, variable frequency control. So within the scalar control strategies, the best control strategy actually that is used in the industries is variable voltage, variable frequency control, and it is fairly simple and it also helps us achieve the decoupling. But the disadvantage associated with this is achieving a V by F ratio as perfectly constant is not practically possible. So while we can do it using the uh, power electronic devices, we can easily achieve the V by F ratio of the constant, but somewhat uh, it may not be practically feasible always to go for V by F ratio to keep it constant, because there might be some impractical values of voltage or frequency that may result uh, uh, out of this scheme. Fine. हमेशा हम वोल्टेज को इतना कम कर देंगे, हम वो फ्रीक्वेंसी को इतना कम नहीं कर सकते. If we are decreasing the frequency beyond the rated value, the losses in the system will increase, or if we are increasing the frequency beyond the rated value, the losses in the system will increase rapidly. Fine. So it's not achieving a perfect constant value is not practically possible. Second disadvantage associated with this is flux control cannot be achieved. इसमें आपका flux constant रहेगा खाली. So if we are actually trying to control the flux, so using variable voltage, variable frequency control, you cannot achieve the flux control. The flux will always remain constant using the variable voltage, variable frequency control. And if flux is constant, that means our efficiency will not be optimized in the system. So in the scalar control strategies, the best control strategy is using the variable voltage, variable frequency control. अब इसमें क्या है कि simply आपको V by F का जो ratio है वो constant रखना है, ताकि आपका जो flux है वो constant रहे. आप speed तो change कर पा रहे हो, but आप flux while you are keeping the flux constant. So that's actually a disadvantage कि आप flux का control नहीं कर पा रहे हो. ठीक है. आप अगर flux को control नहीं कर पा रहे हो तो आपकी जो system की efficiency है वो optimize नहीं होगी. As well as keeping that ratio V by F, it is not perfectly practically possible. Fine. So these are four strategies so far. The fifth scalar control type will be the fifth control strategy will be the scalar stator current control. So we have discussed the rotor current control. Similarly, you can change the stator current as well. Stator current को जब आप कम करोगे, जो आपका जो मैग्नेटिक फील्ड की स्ट्रेंथ होगी वो भी कम हो जाएगी. अगर आपका मैग्नेटिक फील्ड कम हो रहा है तो आपका जो रोटर में इंड्यूस्ड वोल्टेज है वो भी कम हो जाएगा. सो यू आर एक्चुअली controlling the speed of induction motor. So stator control can be achieved by either incorporating stator resistances. स्टैटर वाइंडिंग में एक्सटर्नल रेजिस्टेंसेस आप इंकॉर्पोरेट कर सकते हो, और यू कैन आल्सो to decrease or increase the stator current. And one last type of scalar stator control strategy is the stator voltage, current, and frequency control. So you are actually uh, changing all the three parameters, voltage, current, and frequency together, such that you can actually, while you can also keep the flux constant by keeping the ratio V by F constant. You can additionally achieve further speed range by changing the stator current. ठीक है. तो मैंने जैसे बताया कि वेरिएबल वोल्टेज वेरिएबल फ्रीक्वेंसी कंट्रोल में एक प्रैक्टिकल लिमिटेशन है. आप इतना you cannot always keep on changing the voltage and frequency, uh, but what you can do is you can change the voltage and frequency in such a fashion that the flux remains constant, and simultaneously you are changing the stator current such that speed, uh, there is a possibility of widening the speed variation range in case of the induction motor. ठीक है. तो हमने छह types of stat scalar control strategies पढ़े आज. One is the starter voltage control. Simply जो आप सप्लाई वोल्टेज दे रहे हो स्टार्टर को इन केस ऑफ इंडक्शन मोटर उसको कम ज़्यादा कर सकते हो. You have seen this practically also. You can change the speed of induction motor by decreasing or increasing the voltage input to the induction motor. ठीक है. Second is the starter frequency control. Again, using different frequency converters or using generators, आप फ्रीक्वेंसी इनपुट जो आपके सप्लाई वोल्टेज की इनपुट फ्रीक्वेंसी है उसको कम ज़्यादा कर सकते हो ताकि आपका जो सिंक्रोनस स्पीड है वो चेंज हो जाए और अकॉर्डिंगली आपका रोटर स्पीड भी चेंज हो जाएगा. You can control the rotor voltage or the rotor current by incorporating more resistances. You can incorporate resistances in the starter for starter current control. Fine. And you have the variable voltage variable frequency control method जिसमें आप voltage और frequency के ratio को constant रख सकते हो such that flux remains constant but you are achieving speed control. Fine. And lastly, you can change voltage and frequency to keep flux constant and simultaneously change the starter current. And lastly, you can using the starter voltage current and frequency control, you can keep the flux constant. You can additionally change the starter current to get a wider speed variation range. Fine. So among all these scalar control strategies, the most widely used one is the variable voltage. Uh, and it's actually industry-wise the most widely used control strategy is variable voltage, variable frequency control. Okay. So although vector control has much more advantage as compared to the scalar control strategy, but because of the simple nature of variable voltage, variable frequency control strategy, the most widely used one at present times in the industries is variable voltage, variable frequency control strategy. Right? So this was just today we only saw the overview of variable voltage, variable frequency control. इसकी जो circuit diagram है, how we are going for open loop variable voltage, variable frequency control, how we go for closed loop variable voltage, variable frequency control, how we achieve speed, torque, and flux responses in variable voltage, variable frequency control. That will be the topic for the next session. उसके बाद